Welcome, fellow explorers of the cosmos. You know, ever since Galileo pointed that first telescope to the heavens, we've been on this insatiable quest to understand the universe. And for centuries, we've relied on light, on electromagnetic radiation to bring us information across the vast cosmic ocean. But what if I told you there's another way? Another messenger that can tell us stories hidden from even the most powerful telescopes? Welcome to our deep dive into the advanced aspects of gravitational waves. Today, we'll explore the mathematics, quantum connections, and much more. Fasten your seatbelts, folks, because we're about to embark on a journey to the very edge of space-time itself. You see, Einstein, in his infinite wisdom, gave us these elegant equations, these masterpieces of mathematical thought called the Einstein field equations. Now, these equations, they describe how the very fabric of space-time, the stage on which the cosmic drama unfolds, is warped and curved by the presence of mass and energy. But here's the thing, these equations, they get really complicated, really fast, especially when you're dealing with massive accelerating objects. But there's a trick, a simplification we can use when we're far away from these objects, in the realm where space-time is almost flat. In this regime, the equations, they sing a different tune. They reveal their wave-like nature, and out pops the wave equation for gravitational waves. Imagine, if you will, a still pond. Now, toss a pebble into it. What do you see? Ripples, right? Expanding outward, disturbing the surface. Gravitational waves are kind of like that, ripples in the fabric of space-time. But these ripples, they're not just any ripples. They're special. They come in two flavors, two polarization states, the plus and the cross. Now, imagine you're holding a ring of particles. When a plus polarized wave passes through, it stretches the ring along one axis, and then along the perpendicular axis. A cross polarized wave does the same thing, but it's rotated by 45 degrees. And you know what's amazing? We've built these incredible instruments, these laser interferometers like LIGO and Virgo, that can actually detect these minute stretches and squeezes in space-time. Okay, folks, now let's dive into the deep end, into the realm where gravity and quantum mechanics meet, a realm still shrouded in mystery. You see, in the quantum world, everything, and I mean everything, is quantized. Light, it's not just a wave, it's also a particle, the photon. And just like that, we believe that gravitational waves, they too, are made up of particles called gravitons. Now, we haven't directly detected these gravitons yet, but the math, the theory, it all points to their existence. And here's where it gets even weirder: quantum entanglement. Imagine two particles linked together in such a way that even if they're light years apart, they can still instantaneously influence each other. Some physicists believe that entanglement might play a role in how gravitational waves interact with matter, potentially opening up a whole new avenue to understand the universe. Now, we often think of space-time as this rigid background, this unchanging stage. But that's not entirely true. Gravitational waves, they don't just pass through space-time, they leave a mark, a permanent deformation, kind of like a cosmic bruise. This is what we call the gravitational wave memory effect. Imagine two mirrors floating in space. When a gravitational wave passes through, it stretches and squeezes the space between them, and even after the wave is gone, the mirrors remain slightly displaced. This effect, it's incredibly small, but it has profound implications. It tells us that space-time itself has a memory, that the echoes of these cosmic events are imprinted on the very fabric of the universe. So far, we've talked about gravitational waves from black holes and neutron stars, but the universe, my friends, is full of surprises. What about sources we haven't even imagined yet? What about primordial gravitational waves, ripples in space-time generated in the earliest moments after the Big Bang? These waves, if we could detect them, would be like a direct message from the infant universe, telling us about the conditions when the cosmos was just a fraction of a second old. And then there are cosmic strings, these hypothetical, incredibly dense defects in space-time, remnants of the early universe. As these strings vibrate, They could generate their own unique gravitational wave signatures. Now, close your eyes for a moment and imagine all the gravitational waves from all the black holes, all the neutron stars, all the cosmic events throughout the history of the universe, all rippling through space-time, overlapping, interfering with each other. What do you hear? A faint hum, a cosmic symphony, the gravitational wave background. This background, it's not something we can detect with our current instruments, but future missions, like the Laser Interferometer Space Antenna, LISA, they'll be sensitive enough to hear this cosmic orchestra. And when we do, it'll be like listening to the heartbeat of the universe itself, revealing secrets about its evolution and structure. Black holes, those enigmatic cosmic monsters, they're some of the most fascinating objects in the universe. And you know what's really cool? When two black holes collide, the resulting black hole. It's not just sitting there, it's ringing like a bell. This ring-down phase, it's a prediction of Einstein's theory of general relativity, and it's a powerful test of one of the most fundamental ideas about black holes, the no-hair theorem. This theorem states that black holes are incredibly simple objects, completely characterized by just their mass, spin, and charge. Everything else, all the information about the original stars that collapsed to form them, it's lost forever behind the event horizon. By studying the ring-down phase, we can test the no-hair theorem with exquisite precision, pushing the boundaries of our understanding of these extreme objects. We're standing at the dawn of a new era in astronomy, an era where we're not just looking at the universe, but listening to its gravitational whispers. And the best is yet to come. We have next-generation detectors like the Einstein telescope and Cosmic Explorer in the pipeline, with sensitivities orders of magnitude greater than what we have today. These instruments will allow us to detect gravitational waves from even more distant and exotic sources, revealing the hidden universe in unprecedented detail. And then there's LISA, the Laser Interferometer Space Antenna, a space-based gravitational wave observatory that will be sensitive to frequencies lower than what we can detect on Earth. LISA will open up a whole new window to the universe, allowing us to study supermassive black hole mergers, the dynamics of galactic nuclei, and perhaps even the very first moments of the universe itself. And then there's the great unknown, the dark sector of the universe, dark matter and dark energy. These mysterious entities make up the vast majority of the cosmos, yet we know very little about them. Could gravitational waves hold the key to unlocking their secrets? Some physicists believe that primordial black holes, formed in the early universe, could be a significant component of dark matter. And if so, their mergers would generate gravitational waves that we could detect. Others are looking for gravitational wave signatures from axion clouds, hypothetical clumps of ultralight particles that are another dark matter candidate. The search for dark matter and dark energy with gravitational waves is still in its infancy, but it holds incredible promise for revolutionizing our understanding of the universe's dark side. As we continue to explore the universe through the lens of gravitational waves, we stand on the brink of groundbreaking discoveries. Each ripple in space-time carries with it a story, a message from the distant cosmos, whispering tales of black holes colliding, stars exploding, and the very fabric of reality being stretched and squeezed. The universe is a vast and mysterious place, and we've only just begun to scratch the surface of its secrets.